Okay, with section 10.3 we have 4 new theorems to learn. The first one is in the same circle. I forgot to start with a joke. Sorry, Miss Siski. What did the circle say to the tangent? What did the circle say to the tangent? So our first theorem is in the same circle or in congruent circles, 2 minor arcs are congruent if and only if, remember there's a shortcut for that, if and only if their corresponding chords are congruent. So these 2 chords are in the same circle, and so if these 2 chords are congruent, the 2 arcs are congruent. So arc AB is congruent to arc CD if and only if segment AB is congruent to segment CD. And you want to make sure that I can always tell the difference between an arc and a segment. You want to make sure that it's clear about that. And I know Ms. Siski talked about congruent circles in her video on 10.2. Congruent circles would be 2 circles where the radii are the same. I know she said that already, but since it's in the same circle, obviously that will work. So let's do an example. In the diagram, circle A is congruent to circle D. We know that because this radius is congruent to this radius. And so if BC is congruent to EF, you're given that, and they tell you that the measure of arc EF is 125 degrees, find the measure of arc BC. So there's really no thinking to this. It's just that because the segments are congruent chords in congruent circles, the corresponding minor arcs are congruent. Okay, so the measure of arc BC is equal to the measure of arc EF, and so they're both 125 degrees. Of course, don't forget your label. Here's another theorem. We've got 3 theorems on this first page. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. Now, key here, it's not just perpendicular, it's not just bisector, it has to be both. So if you see 2 chords in a circle, and you can say, oh, look, perpendicular bisector, that tells you that the one that's doing the bisecting is a diameter. So without knowing where the center is, I know that SQ is a diameter. So if segment QS is a perpendicular bisector of TR, then segment QS is a diameter of the circle. Next theorem. It's kind of the opposite of that, that if you see that you have a diameter, now I see the center, I can assume collinearity of points. It appears that this chord is going through the center, so I can assume that EG is a diameter. I also see a right angle. So now that I have a diameter that's perpendicular, I know that it bisects the chord. And so if a diameter of a circle is a perpendicular to a chord, so you have to have diameter and perpendicular. In both these cases, you have to have 2 things to prove the third. Then the diameter bisects the chord. So since segment EG is a diameter and EG is perpendicular to DF, then segment HD is congruent to segment HF. And arc GF is congruent to arc GD. Okay? All right. This is kind of a neat, these theorems really help in real life. Here we go. We have a journalist is writing a story about 3 sculptures. They're arranged like this, and the question is, where should he put the camera, he or she, put the camera so that it's the same distance from each sculpture. If you were, first it says to label them A, B, and C, and if you were to draw segment AB and draw segment BC, okay, now we want to draw the perpendicular bisectors of both segments. Okay, so I'm going to kind of just sketch. I just want to envision here's the midpoint, and I want to draw it to appear perpendicular. Of course, we could construct this with a compass or a mirror or a graphing calculator, but right now I'm just kind of eyeballing it. And so I've drawn that to be perpendicular bisector. I've drawn that to be a perpendicular bisector. And so this point is where the journalist should put the camera. Because of, I hate to say it, I'm going to actually write theorem 10.4, even though we never refer to theorems with numbers, but because of that theorem, the diameters these are the diameters of the circle containing ABC. In other words, this point right here is the center of a circle that would include all three of those points. Find the point where these bisectors intersect. That's what I was just saying. This is the center of the circle through all those points. And so this is the point that is equidistant from each of the sculptures. And they have a nice picture here that the camera should go there. Pretty helpful. So another example, we're going to use a diagram in circle E to find the length of segment BD and then tell what theorem you use. So I can clearly see that this is a diameter, and I can clearly see that it's a right angle. And so that there's a theorem that says if I have a diameter that is perpendicular to a chord, it bisects that chord. So diameter AC is perpendicular to BD, so by theorem 10.5, we know that segment AC bisects segment BD, or diameter AC, either way. And we also know that segment BF is congruent to segment FD. Now notice they don't have segment bars over there, but they also don't have a congruent sign. So they're saying the measure of segment BF is equal to the measure of segment FD. So if BD then would be 2 times 6, or 2 times DF, that's what they want there, sorry. 2 times 6 is 12. So we have no indication of units here, so 12 units would be nice, but they didn't give us centimeters, inches, or anything. So just 12 will work. Okay, last new theorem. In the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Now let's revisit this word equidistant. If you recall from a chapter in the past, it's not just any, you can't draw in any segment from E to segment CD, or you can't draw in any, just anywhere. It has to be a perpendicular distance. The shortest point, the shortest distance between 2 points is a straight line. Well, the shortest distance from a point to a segment would be a perpendicular distance. So the only way for this to work is that if you know that from the center to the chord is we're looking for the perpendicular segment to that chord. So if I know that segment AB is congruent to segment CD, and I can see that I have from the center perpendicular, from the center perpendicular, then I know that since AB is congruent to CD, this would only be congruent if these also were congruent. And that's going to be, you can imagine, this could be really powerful in terms of algebraic problems, because as soon as they give you that diagram, if you know the chords are congruent, you've got these little segments. If you know those little segments are congruent, you've got the chords. So that works out really well. All right, so we're going to take a look at this, and I know the Xerox machine made it kind of light, so we'll try to get through this. In the diagram of circle F, the length of segment AB is equal to the length of segment CD is equal to 12. So chord AB is congruent to chord CD, and they're both 12 units. And you want to find segment EF just from here to here, just that distance right there. Well, since these are drawn in at right angles, if this is 12 and this is 12, that means that FG is congruent to EF. And so we have, now I've made it so I can't even say, oh, this is supposed to be 7x minus 8. And so 7x minus 8 is equal to 3x. That's what we're going to do. But let's fill in what they want us to fill in here. If the chords are congruent, so by that theorem, they are equidistant, which means that EF is equal to GF. Okay, so since EF is equal to GF, that means 3x is equal to 7x minus 8. Of course, you would add 8 to both sides and divide by 7, and you end up with 2. So x is 2. Now that isn't my answer because the measure of segment EF is 3x. So of course you have to do 3 times 2, and you end up with 6, again, units. Would be nice. Okay, here's the part where you hit pause. Before you do, I just want to point out that it was difficult to see that these are arcs. All three of these are arcs. I guess it clearly, we don't have any segments drawn in for CB or BE, but CE has a segment, and so it matters. They're asking for the measure of the arc CE, all of those. So go ahead and pause it and try those 3. Okay, so hopefully this one's really fast. If, this is also arc, if the measure of arc TV is 121 degrees, find the measure of arc RS. Well, in the same circle, this chord is congruent to this chord. How do I know? Because they both have a 6 there. So that means this is congruent to this. Let's just make sure we write a complete mathematical sentence, and that's done. The next one, it took me a little bit of thinking with this one in terms of why this works. We have a theorem that says if I can clearly see that's a diameter and I can clearly see it's at a right angle to that chord, I know that that chord's being bisected. We also can bisect arcs, and so it's also bisecting this arc. So you could say point B bisects arc CE, you could say segment BD bisects the arc, line BD, line segments raise points. You can bisect an arc the same way you bisect a segment. And so then you just go ahead and set up that 4x is equal to 80 minus x. Sorry that I didn't notice that. It was probably impossible to finish this without that. And so we end up with x equals 16. So if x equals 16, that means the measure of arc CB is going to be 4 times 16, or 64 degrees. And then the measure of arc BE is going to be 80 minus 16, or 64 degrees. And so the measure of arc CE, okay, and as Ms. Siskey said, we know we're not going to go this way with the major arc. We always assume that it's a minor arc. Arc CE, we're just going to add those together and get 128 degrees. Last one. In the diagram in example 4, suppose that AB is 27, okay, and EF is equal to GF, which is equal to 7. All right, I'm going to actually redraw that. So suppose that AB is 27, and then EF, as soon as EF is congruent to GF, I know that AB is congruent to DC. And so the measure of segment CD is 27 units. Okay, let's see. The answer to the joke. What did the circle say to the tangent? Stop touching me! I have 2 boys, 2 sons. Stop touching me! I hear that all the time.